Here is an example to axiomatic systems, and it's a very famous axiomatic system that I'm going to talk about. This is the list of Peano axioms. This is for natural numbers, the definition of, let's say, natural numbers. And these were laid out by Italian mathematician Giuseppe Peano. Okay, so these are, well, in their original form, there were slight changes. But in general, in modern mathematics, these are the generally accepted Peano axioms. Okay, so the first one says 0 is a natural number. Okay, that's the first one. So you are actually stating, or you are specifying, let's say, the first ever natural number. Second one, for every natural number x, its successor s of x. Now this is a unary function, s of x. So it accepts one single input and produces an output. And we call it the successor function. For every natural number x, its successor sx is a natural number. So for all x, if x is in natural numbers, then this implies that its successor s of x is also going to be in natural numbers. The third one, two numbers are equal if and only if their successors are equal. Okay, so this is sort of a definition of equality. Remember last week I said that definitions usually include biconditionals. So this you can see this as a sort of a definition. The fourth one, there is no natural number whose successor is 0. Okay, so it's not like cyclic, it doesn't come back. And fifth one is what we call the induction hypothesis. Okay, this is going to be very significant later on. And let's look at this axiom and try to understand what it's trying to say. For all k, now k here is a structure, essentially it's going to be a set. 0 is in k, 0, remember, is our first natural number. And look, for all x, x is in k, implies s of x is in k. That means for any natural number you pick, if that's in the set k, then if this implies its successor being also in k, then this coupled with this, okay, together imply that k in fact is the entire set of natural numbers, or alternatively we can say that k has as elements all natural numbers. Okay, so this is called, as I said, the induction hypothesis or the induction axiom. Okay, so here if you look closely, well, these terms are going to become apparent later on, but this sort of defines your base case, and this one here up to this point is the inductive case, and together they are combined with an and, together they imply that whatever this k is, whatever property it is, it applies to all natural numbers. Okay, so a couple of notes here. As I said, these are slightly different than Peano's original formulation. And in the original formulation, in fact, the first natural number was not 0. Peano chose the first number to be 1. But essentially, that's a convention. That's just a naming choice. So it doesn't really change the structure or the properties of natural numbers, whether you start from 0 or 1. But as you know, modern mathematics accepts 0 as a natural number, so we generally state the axioms using 0. However, in the original formulation, whatever you see here, 0 here, this 0 here, this 0 here, they should all be replaced with a 1. And also, there were 4 more axioms regarding the properties of equality. And today, in modern mathematics, these properties essentially are accepted as part of the equality, let's say, definition, like if x equals y, then y equals x, let's say, or for all x equals itself, etc. X equals y, and then y equals z, this implies x equals z, etc. So such properties intrinsic to equality was, let's say, axiomized by Peano, but today we accept them as intrinsic properties of equality, so they are not listed as these axioms. And finally, the last axiom here, as I said, is the induction axiom. And in Peano's original formulation, it's a second order axiom. So what do we mean by second order? Previously, I had said that there are higher order logics that we do not study in this course. So essentially, this is a proposition, let's say, in second order logic. In propositional logic, we do not have quantifiers. And in first order logic, we have quantifiers that quantify variables. And in second order logic, essentially, we have quantifiers that quantify properties or predicate functions. So here, well, I'm not going to go really further into this, but let me just show what this means. This, instead of defining this with respect to K, a set or a structure, Peano based his final axiom on a predicate, or rather a property, let's say. For instance, if that holds for the first natural number, well, in the original case, it was 1 here, doesn't really matter, as I said. If 1 or 0 has that property, and any number x having that property entails its successor having that property, these two together then implies that all natural numbers have that property. Okay, so this is the induction axiom, and in the second half of today's lecture, this is going to be essential.